Hello friends, here is a question that seems almost too simple. Why does 23 mean something completely different from 32? After all, both numbers use the exact same digits, a 2 and a 3. The only thing that changed is their positions. That one shift in position changed the value from 23 to 32, a difference of 9. This is not an accident or a convention we just memorized in school. It is a precise mathematical system called positional notation, and it is the hidden structure inside every number you have ever worked with. In this video, we are going to pull that structure apart, understand exactly why position carries so much meaning, and then watch the same rule work in binary, the language computers speak. Let us get into it. So what exactly is positional notation? Here is the core idea. In any positional number system, you pick a base, a whole number greater than 1. Then you write digits in a row, and each digit's actual contribution to the total depends on two things, the digit itself and which position it sits in. Positions are counted from the right, starting at 0. The rightmost digit sits at position 0, the next one left is position 1, then position 2, and so on. To find what each digit is worth, you multiply it by the base raised to the power of its position. So a digit at position 2 is worth that digit times base to the power of 2. That single rule, digit times base to the power of position, is the entire engine. Everything else we cover in this video is just that rule applied to different numbers and different bases. Let us put that rule to work with a number you already know. 4,362. Written out. That is 4,362, 4 digits sitting side by side in base 10. Reading from the right, the 2 is at position 0, so it contributes 2 times 10 to the power of 0, which equals 2 times 1, giving us 2. The 6 is at position 1, 6 times 10 to the power of 1 equals 60. The 3 is at position 2, 3 times 10 to the power of 2 equals 300. And the 4 is at position 3, 4 times 10 to the power of 3 equals 4000. Add those together, 4,000 plus 300 plus 60 plus 2, and you land right back at 4362. Nothing was invented. We just made the hidden structure visible. Now here is the exciting part. That exact same logic works for any base at all, not just base 10. Now let us change the base, and watch the same rule hold up perfectly. Take the binary number 1011, that is base 2, so the only digits allowed are 0 and 1. Reading from the right, the rightmost digit is 1 at position 0. 1 times 2 to the power of 0 equals 1. Next is 1 at position 1. 1 times 2 to the power of 1 equals 2. Then 0 at position 2. 0 times 2 to the power of 2 equals 0. And finally 1 at position 3. 1 times 2 to the power of 3 equals 8. Add those up, 8 plus 0 plus 2 plus 1, and you get 11 in decimal. Binary 1011 and decimal 11 are the exact same quantity, just written in different bases. The rule did not change at all. Digit times base to the power of position. Only the base number changed. And that universality is exactly why place value is so powerful. So why does this matter beyond the classroom? 2 reasons. First, computers store and process every number in binary, base 2. Every image, every calculation, every file on your device is ultimately a sequence of bit positions, each one contributing a power of 2 to a total value. Understanding place value is the foundation for understanding how hardware actually works. Second, position errors are real and costly. Look at our binary number from the last slide. 1011 in base 2 equals 11 in decimal. But if one bit shifts and the number becomes 1101, that equals 13 in decimal, a completely different value, just from one position change. In software networking and data storage, misreading a single bit position produces silent errors that can be very difficult to trace. Place value is not abstract. It is the difference between a correct result and a wrong one. And it all comes down to that one rule. Let us bring it all together. Every number system built on positional notation, whether base 10, base 2, base 8, or base 16, runs on exactly one rule. The value of any digit equals that digit times the base raised to the power of its position, counting from 0 on the right. We saw it decompose 4,362 into 4,000 plus 300 plus 60 plus 2. We saw the identical rule convert binary 1011 into decimal 11. The base changed. The rule did not. Here is your takeaway. Next time you see any number, ask yourself what base it is in, identify each digit's position, apply digit times base to the power of position, and add the results. That is all there is to it. Try it with base 8 or base 16, and you will see the same principle hold every time. Thanks for watching. See you in the next one.